So it's a great pleasure to introduce Dr. Florian Pausinger from Queen's University, Belfast, who will talk about long shortest vectors in low-dimensional lattices. Over to you, Florian.
Hello, yeah, thank you for letting me speak here. And after having studied the program, I see that I'm an outlier here. So I think it's the only talk not about persistence. And the story is that Vitaly asked me to speak about lattices, which I happily accepted because I really like to talk about lattices. So yes, that's the setup. I guess outliers motivate persistence homology. So that's how I can close the circle. Okay, so what I'm going to talk about today is work I have done during lockdown last year. And it's about shortest vectors in low dimensional lattices. So with low dimensional, I mean dimension 2, 3, 4, and 5. Okay, so the start of my investigation was this particular kind of point set. So I denote them with this capital pi. And I was interested in these three-dimensional point sets where you basically choose 3 integers, a, b, and c. And then you have an index n that runs between 0 and capital N. And you take integer multiples of your index n with your different generating parameters a, b, c. You reduce them modulo n. So if the greatest common divisor of n and a is 1, you always get a set of n different points in the 3-dimensional unit cube. And of course, you can study such point sets also in 2, 4, 5 dimensions by just adding more parameters or more coordinates. And given such a point set, and I will illustrate it in a moment, one can look at the shortest distance between any 2 points in your point set. So I will denote the shortest distance always with a lambda star. It's defined as the minimum over all pairs of points in your point sets, and you look at the distance between these points. And what I would like to ask today is, how long can the shortest distance between points of such sets be, independent of your number of points capital N? And how can we explicitly construct sets with long shortest distances? So these are 2 examples of typical point sets. So you can imagine, so this is just in 2 dimensions because it's easier to illustrate. The point 0, 0, 0 is always contained in our point sets because we allow the index n equals 0. And then you have your parameters. Let's say this is the point you get for n equals 0. Then maybe this is the point you get for n equals 1. And then you look at all the integer multiples. You take them modulo n. So basically you have here a line that you take mod n and that runs through this square. So these point sets still look quite simple, and I have illustrated here the shortest distance you can find. So you can see that the shortest distance can actually either be an element of the point sets, as in this case, or it can just be a new vector. So this vector is not an element of the point set itself. You have here a point of the set and here a point. This is the difference. But yeah, it's not an element here. Things can get much more complicated, as you can imagine. For example, we can look at a point set with 244 points and the generating parameters 13 and 169. And then I have colored the first 13 points of this point set in red. So for index 0, we get the origin 0, 0. For index 1, we get the point 13 and 169. For index 2, we would get this point here. For index 3, we go all the way up and come back in here and so on. And now if you're looking at such a point set, it's already not so clear anymore how to actually find out what the shortest distance is. So In this case, of course, it would be the distance from the red point to the first point here, but how to find it algorithmically is not so clear a priori. Now, before going into more details, we can give a quite easy heuristic bound on the length of such a shortest distance in these lattices. So by our definition, so I had this this condition that the first parameter has to be co-prime to the capital N, and the other two parameters have to be different from A. So one can quite easily find out that the shortest possible distance between 2 points in the three-dimensional set contains 1, -1, and ±2, which gives a distance. So the length of this vector is square root 6. So the shortest distance between points can actually be a constant that is independent of n. But what is about the other end of the spectrum? So what is an upper bound? And here I can just draw a two-dimensional example for you, what the argument is that gives the order of magnitude. So we can imagine that we start here in the point 0, and then we have, let's assume this is the shortest distance between 2 points. So this would be the lambda star we are interested in. Well, then it's clear that in the two-dimensional case, a quarter circle around the origin cannot contain any other point of our point set because this is the shortest distance. And we can attach now such a quarter of a circle to each point in our lattice. And since we know the volume of the whole unit square, and we know the number of points, we can easily use this kind of volume area argument to get an upper bound of the length of the shortest distance. In the three-dimensional setting, the upper bound is of order n to the 2/3 with a constant c that is unspecified for the moment. So the longest, shortest vectors we can hope for are of order n to the 2/3. Okay, so as you can imagine from the title of my talk, lattices play a very important role in finding out how to get sets with very long shortest vectors. And I'm sure everybody knows, if we start with d linearly independent vectors in Rd, then we can use them to generate a lattice. So the lattice is just given as a point set in which you take these linearly independent vectors, the spaces of Rd, and multiply it with integer vectors. So the lattice denoted as capital lambda of the basis V is just the set of all vectors that you get from the multiplication of the basis with an integer vector. And of course, the set V is called the basis for the lattice. Now, the first interesting notion here is that two different bases, V and V prime, generate the same lattice if and only if there exists a unimodular matrix U such that one basis can be transformed into the other basis via matrix multiplication. So just to recall, unimodular means that the determinant is 1 and the entries of the matrix are all integers. Now, this property motivates to define the so-called co-volume of a lattice, which is simply denoted as the volume of the lattice generated by V, and which is just the determinant of the matrix of the basis vectors. So this MV is just the square matrix whose rows are the basis vectors. And this is a characteristic quantity of each lattice, which is independent of the particular base that one chooses because of this unimodular matrix with which you can switch between bases. And another very classical notion in the context of lattices is the so-called ith successive minimum lambda I, which is the radius of the smallest closed ball centered at the origin that contains at least I linearly independent lattice vectors. So I have tried to illustrate this here. So if this is our point 0, 0, then we can grow a circle around 0, 0 until we reach the first point of the lattice. And the vector connecting the origin with this first point would be the vector giving you the first successive minimum. Then if we grow the ball, the radius of the next circle that contains the second linearly independent lattice vector gives you the second successive minimum. And in particular now, the length of this first successive minimum is exactly the length of the shortest vector of the lattice lambda. So this is just terminology or a different way to look at it. So you can just grow a ball around the origin, and you can take the length of the first linearly independent vector you find of the second, and so on. And the final notion I want to introduce here is the so-called Hermite constant of a lattice. So this is usually denoted with a gamma and subscript d for the dimension of the lattice. And this Hermite constant is defined as the supremum over all lattices in a given dimension. And here you divide the length of the shortest vector by the dth root of the volume of this lattice. So basically, this is a normalization because you go over all the lattices. You look at the shortest vector divided by the co-volume of it. And this is a very interesting constant. It's an upper bound on the maximal length of short lattice vectors in Euclidean space, and it is only known for very particular dimensions. So it is known for dimension 1 to 8, as well as for dimension 24. And this number is also directly related to lattice packing problems and so on. So yeah, it's a very interesting notion in lattice theory. Now, in the following, I would like to restrict to 3-dimensional lattices, and a basis of such a lattice is called a Minkowski-reduced basis if it satisfies 2 conditions. So first of all, you can order this the length of these vectors, which is not a big deal, but the other condition gives you certain inequalities on the length of the vectors. And the motivation behind this notion is that the shortest vector of a reduced lattice basis is always the shortest vector of a lattice. And there are algorithms that allow you to calculate a Minkowski reduced basis for a given lattice. So for example, for 3-dimensional lattices, there are different algorithms that output you a reduced basis. You can even do that in Mathematica. It's just a standard function there when you are working with lattices. Okay, oh, wrong direction. So with all this background on lattices, I would like to return to the original point sets I was interested in. So the point sets that I introduced can be obtained, which is not surprising, as intersections of the cube in which they are defined with an underlying 3-dimensional integer lattice. And now if we just restrict to this particular form of generating vectors, so I just set the first parameter a equal to 1, which is only a very mild restriction, then we get particularly simple generating matrices for the underlying lattices. So if we have this parameter vector 1 bc, then the point sets I introduced can be generated from the lattice of with this generating matrix intersected with this three-dimensional cube. Okay, so this is very important to work with this particular point sets. And the second important observation now is that for a given point set, we can write now lambda of the point set for the underlying lattice, and it turns out, also not surprisingly, but is a bit trickier to prove actually, that the shortest distance in our point set is exactly given by the shortest vector of the underlying lattice. So when I'm interested in my point sets, and in shortest distances of my point sets, what I really have to look at are the shortest vectors in the underlying lattices. So this is already very useful because it relates these point sets to a big body of theory in the back. Now, just for an illustration, so the green points would be a two-dimensional instance of the point sets I'm interested in, and the blue points around should give you an idea of the underlying lattice of this green point set. And this, of course, generalizes to other dimensions. Okay, so now remember that in the beginning, I gave an intuitive argument about the order of magnitude of this shortest distance. And now I would like to go one step further and also determine the leading constant that we have. So I had c times n to the 2/3. And this goes back actually to very famous work of Gauss, who showed that the face-centered cubic lattice, the FCC lattice, gives the densest sphere lattice packing in R3. And later, it was also shown that this actually gives the densest packing among all lattices. So this is the famous Kepler conjecture, which was recently resolved. So now if we think about a packing problem, the shortest vector in an FCC lattice is exactly twice the radius of the spheres which are centered at the nodes of the lattice. So the idea here is that you have this FCC lattice, and each lattice point is the center of a sphere. And if you arrange your sphere exactly according to the points in your lattice, then you manage to put as many spheres as possible into a given volume. So this is the problem of lattice packing. Now, the FCC lattice can be built out of basic cubes. So if this is a cube, then it can be shown that the points in the FCC lattice are always lying at these 4 vertices of a cube. And between each pair of points, you have exactly this distance L, which is the shortest lattice distance here. Now we know that we want to distribute capital N points into a volume of into a cube of volume n-1/3. So we can now look for the maximal number L such that we fit our cubes into this volume, and this gives us an approximate idea of what we can expect. So if we use this argument of best possible lattice packing, well, we know we cannot be better, and so the longest vector to expect is approximately of this length. Now we can work out, because we already know the order, so we can work out the constant, and what we get is a constant of 2/1/6. And this actually makes a lot of sense because we can go back to the Hermite constant. Remember that the Hermite constant actually gave you precisely an upper bound of shortest vectors in lattices, and in the 3-dimensional case, this constant gamma 3 is 2⁻⁻3. So if we work out all the quantities that we have, then we get that an upper bound on our L star has to be indeed 2⁻⁶ n to the 1/3. So what I'm trying to say here is that on the one hand, we can get a precise upper bound using the Hermite constant, and on the other hand, using this optimal lattice packing, we can also get an intuitive idea why we can expect to construct lattices that actually satisfy this constant. So this is just to give you a bit of an idea. So this was the setup of the problem. I was wondering what's the longest possible distance between points in my set, and then there is all this theory about lattices in the back. And from all this theory, I can conclude that the best I can hope for is actually a lattice distance of 2 × 1/6 times this constant independence of the number of points. And now the question is whether such point sets really exist or whether this upper bound is loose. So I started with some numerical observations. So what I did was I just looked at this parameter vectors 1bc, and I constructed all possible lattices for a given n. I checked them for their shortest distance, and I plotted the best value that I received for each n. So the green line here is the value you get from the Hermite constant. The second green line here is at 1. So this is what a cubic lattice would give you. And in between, all these dots correspond to the longest distances you get for a particular n. So for example, if we are here at the 160, then the longest distance would be approximately 1.08 and so on. So what you can see is that for every n, there seems to exist at least one point set that has a clearly larger shortest distance than a cubic lattice, but still the points are far away from the theoretical upper bound. So in the beginning, I was not very hopeful that there are actually lattices that can achieve this optimal upper bound. Now, this was the 3-dimensional setup. One can ask the same question in 2 dimensions, which I actually did several years ago. And with a similar heuristic, one can derive also similar results here. So in 2 dimensions, we have the hexagonal lattice that maximizes the packing density in R2. So the hexagonal lattice can be defined in this way. Now we can define our point sets analogously, and we also define the shortest distance lambda star for these point sets. And it turns out that with a similar volume argument, we get that L lambda star has to be upper bounded by square root n times the square root of the Hermite constant. And what was very striking in 2 dimensions was that there existed a construction based on continued fractions. So you have a particular number of points, and you choose a particular generating parameter. So this, this ratio has a very, very structured continued fraction expansion. And for a miraculous reason, if you generate this integer lattice with this basis, it turns out that the normalized length of the shortest distance converges exactly to square root of the Hermite constant in 2 dimensions. So there are several interesting aspects here. First of all, it seems that this type of lattice approximates the hexagonal lattice asymptotically. So the more you increase the S, the larger the capital N gets, which is the number of points, and the closer you get to a perfect hexagonal lattice. Now, the downside of this approach is that it relies on continued fractions expansions, and this notion typically only exists in a meaningful way for fractions and not for pairs of fractions. So there are all kinds of notions of multidimensional continued fraction expansions and so on, but nothing really helps to generalize this idea here, because as soon as you go from 2 to 3 dimensions, there is some additional structure added that I just do not see how to capture with continued fractions, and therefore I actually never continued until the lockdown came and I was really bored. So the interesting thing is, as you might guess, because I'm talking about it, in the end, I managed to construct lattices whose normalized shortest distance is really arbitrarily close to this theoretical upper bound. So the theorem I managed to prove, and I will show you in a moment how I did that, is the following: that for every epsilon greater 0, there exist infinitely many pairs n and v, so v is the generating vector, such that the shortest distance lambda star divided by n to 2/3 is greater than this theoretical upper bound minus epsilon. So I can always find pairs n and v such that I can generate lattices so that this ratio is arbitrarily close to the theoretical upper bound. So these lattices converge nicely to the FCC lattice. And what I have already mentioned, so in the beginning, from numerical observations, it seems that this is not possible. So the up to n equals 310, the best lattice I found was for parameters n equals to 244 with this generating vector 113 and 169. And I did not understand for the longest time why this lattice was so particularly good, and also why it was so rare. But as you can already see, this vector has actually a lot of structure. So this is 1, 13, and 13 squared. So I experimented a lot with different kinds of constructions, all based on this example that I found here. And eventually I came up with a construction that actually worked in general. However, before talking about this, so I also want to mention that I found a similar construction such that the normalized shortest distances always converge to 1. So my first construction in a way approximates the FCC lattice, while the second family of lattices somehow approximate the cubic lattice. And just to show you why 1 is really the right thing here, we can look at a typical cubic lattice. So we have n equals n small n cubed many points, and we can generate a cubic lattice with these generating matrices where we have a small n square in the diagonal. We multiply this with integer vectors, we intersect it with our cube. So this gives a nice cubic lattice. And now if we look at the co-volume, which is the determinant of this matrix, and if we plug it in here, we get an n square, and the shortest distance in this lattice is obviously n square as well. So overall, we get a 1. So if we find lattices that also have a value 1, then they usually approximate the cubic lattice. Okay, so going back to my numerical approximation, there is this one open problem that remains. I think it's true, but I don't know how to show it. So prove that there exists an absolute value epsilon such that for every n that is greater than a given constant, there is a generating vector such that we have a lattice that is strictly better than the cubic lattice. I mean, from the numerical observation, it is clear that for every n, we find such a lattice. I just don't know how to prove that, how to really show it for every n. Okay, so the first construction I found goes as follows. we start with an integer m, and we take capital N equals m to the power of 3 minus 1 many points, and we choose a parameter vector of 1, m, and m square. And then it can be shown that lambda star, the shortest distance in our point set, is the square root of 1 plus m square plus m to the power of 4. We know from the lemma I have shown you in the beginning how this point set can be generated. It's basically you have the vector 0, 0, n, 0, n, 0, and the third column would be 1, m, and m squared. So it's very easy to calculate the determinant of this matrix. And together with the information on the shortest distance, we get indeed that if m goes to infinity, we get 1. So we can work out here, we have m3 and we take it to the power 2 over 3. So we have an m square here. And also we can see that this term is of order m square. So we have roughly m square over m square, which gives the 1. Okay, so this is one way of generating infinitely many lattices or point sets that look similar to the cubic lattices. Now, the second construction looks very similar. So we start with a parameter b, which is an odd integer. It's given as 2k plus 1. Now we have capital N many points of, and this n looks as b to the power of 3 minus 1 over 2. And we start again with a parameter vector 1, b, and b squared. And interestingly, one can also work out that this ratio looks like this for a given k. So the k relates to the p, and this ratio is indeed 2 to the 1 over 6. So this is exactly the Hermite constant. So indeed, as we go with k to infinity here, if we construct lattices with these parameters, we get that the shortest vectors of these lattices are as long as possible. And the proofs are not that difficult. The really hard part is to come up with the lattices in the first place. So what we do here is we basically, let me go back. So I have shown you this lemma that gives you a generic basis for my point sets. And now we basically have to reduce this generic basis to a Minkowski reduced basis. So I have told you there are algorithms for that. The problem is that these algorithms usually rely on the Euclidean algorithm and other number theoretic algorithms, which are usually not having a nice closed form. So all these problems can be solved algorithmically, but it's usually very hard to write down explicit closed form solutions to this type of problems. And so the main task here was to actually come up with the reduced basis and then afterwards prove that this is indeed a reduced basis. So, but once one has these basis vectors, one can just show that they form a reduced basis by checking the conditions I showed you in the definition. So with these three vectors, we can show that they indeed are a reduced basis for the lattice that we get from the lemma I showed you and from the different parameters. And similarly, one can also show the other theorem in that way. So just find the reduced basis and prove that it is indeed a reduced basis. So to go back to my numerical experiments, the green line is again the value you get for the Hermite constant. This red dashed line is this very particular lattice with 244 points that I said that performed exceptionally well. And the blue curve here is what you get by using the construction that I suggested. So on the x-axis, you have the parameter k, and we know that asymptotically, these lattices converge to the green line. But you see that you need to go up quite a bit before you actually improve this very particular lattice with 244 points. So one can work out the details, and one needs actually to go to k greater than 31, which is around here. Or in other words, one needs a lattice with n greater than 137,000 points in order to improve this very particular lattice with 244 points. But nevertheless, it is possible to improve it, and it's actually possible to get lattices that are having shortest vectors that are as long as possible. Okay. So in the last minutes of my talk, I just want to point out that this construction also works in 4 and 5 dimensions in a quite straightforward manner. So one can define point sets, one can define shortest distances, generating vectors, and interestingly, one can use exactly the same reasoning to get the right order of magnitude of these shortest distances. One can use Hermite constants to work out the constants one would expect. And finally, one can generalize the construction in a very straightforward manner to actually also show similar convergence results. So now I have lattices in 2, 3, 4, and 5 dimension that give me the longest possible shortest distances. And the reason why I stopped here with dimension 5 is an underlying computational obstacle. So for some deeper reason, as soon as you go to more than 5 dimensions, these matrix reduction algorithms run into several problems, and it's actually not so easy anymore to find reliable reduced bases. So that's why it seems that I am stuck with the first 5 dimensions here. Okay, so with this, I would like to thank you. So this talk was based on 2 papers. So the first appeared in Elemente da Mathematik, which is this general audience journal that usually publishes like semi-serious results. This was for the 2-dimensional problems, and then last year I looked into the 3-dimensional problems, and I got this second paper. Okay, thank you.
Thank you, Florian. Okay, very good. So questions? Oh, Jason, you're muted.
Oh, that was it was a very nice talk, thank you, but that was not mentioned to be meant to be missed.